Hello, my name is Ethan, and this is my fourth project for my fluid mechanics course. And in this video, I'll be doing part A. As you can see, I've already done the system for the project, and now I'm just going to go and walk through how I achieved those results. So I'm going to create this new system. I'm going to call it the same thing, wind tunnel unobstructed video example. Okay, and then I'm going to go into geometry and select new design modeler. Okay, so now that I'm in the design modeler, I'm just going to go over to lines and I'm going to create three sets of lines, one, two, and three. And I'm going to dimension each of these. And this first dimension is going to be 1.1176 meters. The second one should be 1.2192 meters. And the last one will be 1.5748 meters. So as you can see, that shifted them very, very far from the origin. So I'm going to select the middle one, go to constraints, midpoint, and select that origin. And there you go. As you can see, it's back at the origin. So the test section should be at the origin where any objects or things you want to put in the wind tunnel will be at 0, 0. Okay, so now I'm just gonna draw three vertical lines. It actually should be four vertical lines. Okay, so now that I have my vertical lines, I'm going to dimension each of them. This first one should be 1.6256 meters. This second one should be 0.6096 meters. This third one should be the same, 0.6096 meters. And this last one should be 0.889 meters. And now I'm going to grab each of them, select constraints, midpoint, and place them down where they should all be. All right, so as you can see, I have all of my lines in order, and my last step is just to connect all of them. So I'm going to select line and draw. And so now we have our completed outline for our wind tunnel. And the last thing that I'm just going to do is I'm going to go to concept, surface from sketches. I'm going to select all of my outside lines. And click apply, and then click generate. All right, so now that I have my surface generated, I'm going to go back to the workbench and I'm going to edit our mesh. All right, so now that I'm in mesh, I'm just going to first name all of my edges. So I'm going to select the top and bottom. And these are going to be called tunnel walls. I'm going to select my left-hand side, and this will be called velocity inlet. And my right-hand side, which will be just outlet. And so now I'm going to go to mesh. I'm going to select method, and then I'll select the entire face, click apply, and I'll go down to method and I'll select triangles and I'll click generate. And so we can see it's generated a very basic mesh, but we're going to make that more defined and click sizing. We'll select the face, and then we'll go down to element size. Um, and we are actually going to define our element size as 0.005. And then I'll click generate. All right, so now our mesh has completed generating. You can see it's an extremely fine mesh. It will give us a pretty accurate answer, especially with such a small element size. So I'm actually done with our mesh now. So I'm just going to go to mesh, click update, and now I'm just going to go to setup. I'm going to select double precision for processors and click start. All right, so now that I'm in the CFD solver, I'm just going to make sure that we're pressure-based, steady with 2D planar space, and everything looks good there. I'm going to go to model. I'm going to edit our model. We are going to be using a K epsilon model. And then I'm going to select enhanced wall treatment and pressure gradient effects. And now I'm going to move on to our materials. We're going to use standard air, and I'm just going to make sure that everything looks correct. Yep, that's correct density and correct viscosity. So I'm just going to click close. I'm just going to double check that our model is going to be using air, and it appears to be. And now I'm going to move on to our boundary conditions. So for our velocity inlet, we use an equation to get the 15 meters per second in the test section. And that equation is A1V1 equals A2V2. Of course, here we're using heights instead of areas. So that is defined a little bit differently. But because of that proportion and that equation, our velocity inlet is actually going to be 5.625 meters per second. And I'll click apply there. And I'm just going to go through all of my other boundary conditions just to make sure that everything looks correct. The outlet should be a pressure outlet. Yep, looks correct. And they're stationary, no slip. Perfect. So now I'm going to go down to reference value. I'll select velocity inlet from compute from. All of our values look correct. I'll select surface body for reference zone. For methods, we should have coupled least squares, second order pressure, and a second order upwind momentum. And finally, I'm going to go to initialization, and I'm going to use 30 iterations. And then last thing I'm going to do is click run calculation, and I'm going to use 750 iterations and click calculate. All right, so now that our calculations are complete, I'm going to go down to graphics. I'm going to select contours. I'm going to create some new contours. Our first one is going to be velocity. Make sure to select that and velocity magnitude. And I'm just going to take it from all of these surfaces. And so as you can see over here, we have our velocity contours. And now I'm going to create another contour for pressure using static pressure and all of our surfaces. And here is our pressure contour. Our third contour is going to be our total pressure. Once again, selecting all surfaces. And there's our total pressure. And our last contour is going to be dynamic pressure. And there you go. That's our dynamic pressure contour. And I'm going to also create our streamline. So I'm going to call this streamlines. I'm going to color by velocity, velocity magnitude, making sure to select velocity inlet, and I'm going to do 5,000 steps. And so now you can see all of our velocity contours, or I'm sorry, our velocity streamlines. They're very thin and small, but they're there. And as you can see around this the test section, the average velocity should be, at least at the entrance, should be 15 meters per second. Of course, as the test section lengthens, some of that energy will be lost through the wall friction. So roughly around the center, it stays at like 14.9 something. So it is still roughly 15 meters per second, though. And so the last thing that we're going to do is all of our plots. So I'm going to create a new plot. My first one's going to be called tunnel centerline velocity. We're going to make sure to use velocity magnitude. And I'm going to create a new surface and a new line. And so for our endpoints, I'm going to use negative 1.7272 and positive 2.1845. And these values correlate with the beginning and the end of the test section. And this is going to be called centerline. Create that and close. So I'm going to take the velocity magnitude along the center line, and we will see that plot. Yep, so as you can see, we start out at roughly our inlet velocity of 5.625 meters per second, and that rises up because of the converging walls. The pressure lowers and the velocity increases until we get to the test section where it stays roughly at 1.45, 1.9 meters per second. And so that's our first plot. We're going to do a second centerline plot. This is going to be called tunnel centerline pressure. We're going to choose pressure, static pressure, choose our center line, and click Save. Yep, so you can see the static pressure decreasing as the uh, wind tunnel converges, and then it increases back after the test section. And now our third centerline plot. And this is going to be for total pressure, making sure to select total pressure and centerline. And so as you can see here, I believe our CFD solver doesn't know exactly how to show this data. So I'm gonna go back to this later and I'll show you in Excel what I did. And our final XY plot is gonna be tunnel center line dynamic pressure, making sure to select dynamic pressure, center line, and save plot. And you can see that it's almost the opposite of the regular pressure, where it increases and then goes back down at the end. So those are all of our centerline plots. And next I'm gonna do our vertical plots, vertical being along the vertical slice of the test section. So I'm gonna go to XY plots. Here I'm gonna make sure that well, first I'm going to create a new surface and a new line. This is going to be called vertical line. And here our coordinates are negative 0.3, 0.48 to positive 0.348, 0.48. And I'm going to create that. And so we have our velocity. We're going to make sure we're using velocity, magnitude. I'll use the vertical line. Here we're changing our position from x-axis to y-axis, and our x and y plot direction should be changed as well, making sure to re-update this function. And as you can see, as the position varies across the test section, um, you can see the where the wall and the boundary layer affects our velocity. And for the most part, if you take the average of this area right here, it averages out to about 15 meters per second. And so I'm going to do the same thing for um, total pressure, making sure to use the Y, changing our values here. Pressure, total pressure, and selecting vertical line. And you can see it's not unlike the velocity profile, just with different total pressure numbers. And our last plot is going to be for dynamic pressure. All right, and there's our final plot for dynamic pressure. And so I'm just going to go into Excel and show you. So I took all of those plots. I exported them to Excel. I sorted them and you know made sure all of the data sets worked. So for like centerline pressure, all of the centerline plots, we have X going from the start of the test section to the end, and all of those Y data sets are the pressure, velocity, total pressure, and dynamic pressure, respectively. And so as you can see over here are our charts for those sets of data. Um, so we've got our centerline pressure variation, our centerline velocity variation, where it reaches almost to 15. Our so here, no matter which way I organize the data, for total pressure, it just stayed, roughly at um, 58 pascals. So I believe, this is just the what the CFD base outputted. Um, it could be wrong, but it's just what I have. And then, of course, we have our centerline dynamic pressure variation along the center line. And our last three graphs are for the vertical distribution. So you can see that vertical velocity distribution, pressure, or total pressure, and our dynamic pressure. And I believe that's it. Thank you.